Hello students, myself KC Risha, working as assistant professor in mechanical department in MBR College of Engineering and Technology. Today we are going to discuss the topic of critical radius of insulation, and here the words are exactly not visible, but this is the critical radius of insulation, and this is the last topic in our first unit. So this is very important topic in first unit. So first of all, we should know what is the critical radius of insulation. So what is the critical radius of insulation? A material which retards the flow of heat with reasonable effectiveness is known as insulation. So insulation serves the following two purposes. It prevents the heat flow from system to surroundings and prevents the heat flow from surrounding to system. So first of all, the insulation, the meaning of insulation, we all know the exact meaning of insulation is that is nothing but it is a prevention, the prevention of the heat flow from system to surrounding and surrounding to system. The best example I want to give, we are using a material like a thermo flask, so we are providing some insulation around the flask. It provides it prevents the heat from surface to system and system to surrounding. So the basic exactly meaning of insulation is nothing but it prevents the heat from system to surrounding and surrounding to system. So that is the exact meaning of insulation. But here but here the addition of insulation material on a surface does not reduce the amount of heat transfer. Okay, here in a critical radius of insulation, what is the critical radius of insulation is nothing but whenever we are provided some insulation, actually what it is doing, it prevents the heat flow from system to surrounding and surrounding to system. But here, when we provide a when you provide a insulation on the given system, it does not prevent them, it does not prevent them uh, it does not prevent the heat flow from system to surrounding. Why? Because of we are taking a cylindrical systems. In cylindrical systems, when we providing insulation, it does not prevents the heat flow from system to surrounding. So here, when we added an insulation material on a surface, it does not reduce the amount of heat transfer rate always. So in fact, under certain conditions, it actually increases the heat loss. It actually increases the heat loss up to certain thickness of insulation. Okay, so the radius of insulation for which the heat transfer is maximum is called critical radius of insulation. I want to tell in one word, students. First of all, when we take a cylindrical shape, when we so here, what is the exact meaning of critical radius? Actually when we provide insulation, it prevents the heat from system to surrounding and surrounding to system. But in this case, when we added insulation, it does not prevent the heat flow from system to surrounding and surrounding to system. It increases the heat flow. Actually, when we provide insulation, it decreases the heat flow. But in this case, when we provide the insulation, it does not decrease the heat loss, it increases the heat loss. Okay, it increases the heat rate. Okay, it increases the heat rate. So when will it decrease the heat rate? So when we provide addition of insulation after certain thickness, it decreases the heat loss. After certain thickness, it decreases the heat loss. So whenever we have a certain thickness, it decreases the heat rate. We called as a critical radius of insulation. At certain thickness, of insulation, that we call as a critical radius of insulation. So that is the meaning of that. So the addition of insulation material on a surface, it does not reduce the amount of heat transfer rate always. In fact, under certain circumstances, it actually increases the heat loss up to certain thickness of insulation. The radius of insulation for which the heat transfer is maximum is called heat radius of insulation. So after a certain thickness, it decreases the heat rate. So at that condition, is the heat transfer is maximum is called the critical radius of insulation, and the corresponding thickness is called critical thickness. If the thickness is further increased, the heat loss will be reduced. heat loss heat loss will be reduced. And okay, so when we are providing the insulation is added, heat is increasing after certain thickness. After certain thickness, the heat is maximum, heat rate is maximum. After the heat rate is maximum, when now the heat rate is maximum, at that condition we call as a critical radius of insulation. If we add, if you add extra insulation after the certain thickness, after that it will decrease the heat loss. Okay, so whenever the heat is maximum, it called as a critical radius of insulation. At the thickness is called critical thickness. After the critical thickness, it decrease the heat loss. Okay, now so here critical radius of insulation for a cylinder. So this is the critical radius of insulation for a cylinder. This is R1, and around that cylinder is called as the insulation. And this radius of cylinder is R1. The insulation of radius is R2. The difference of R2 minus R1 is called as the thickness of insulation. Thickness of insulation. So this is a solid cylinder, and this is a outer surface. Heat transfer coefficient is H1, and this is a thickness T. So the solid material having the thermal conductivity K. Okay, actually, what do you know? Consider a solid cylinder of radius R1 instead with the insulation of thickness R2 minus R1. So difference of radius we call as a thickness, as shown in the figure. Let L is equal to length of cylinder, T1 is equal to surface of cylinder, and Ta is nothing but temperature of air. Ha is equal to heat transfer coefficient at the outer surface of the insulation. K is nothing but thermal conductivity of insulating material. Okay, the rate of heat transfer from the surface of the solid cylinder to the surrounding is given by this is already done in the in our classroom. In our classroom, what do you know, that q is equal to delta T by thermal resistance. Here here inside, what we have here inside is solid to solid is a conduction takes place, and this is a solid to surface, solid to air, convection takes place. So finally what we have, that q is equal to delta T by thermal resistance. Here thermal resistance are two thermal resistance we have occurred. So one is a conduction, and another one is a surface to area is a convection. So Q is equal to temperature difference is T1 minus Ta by conduction for cylinder is log of R2 by R 2 pi KL plus 1 by H naught into 2 pi L into R2. So that is the thermal resistance. Already be done in this is the equation. Just look at our notes and easily have to understand. Okay. So here from the above equation, that R, that here we are what we are increasing, say R2 radius is increases. So whenever increases the R2, the term log of R2 by R1 by K is also increases. So but the factor H2 H naught into R2 decreases. Here providing insulation extra, that is R2 increases, the term total log of R2 by R1 by K is increases, but the factor H1 by H0 into R2 decreases. So finally the total term thus it becomes maximum. Here finally this is increases and this is decreases, the finally the total term is total terms is maximum. So when the denominator become minimum, so thus it becomes maximum when the denominator becomes minimum. So the required conditions. So understand, this is increases and this is decreases. The total term is minimum. So the required condition is d by, with respect to, we are increasing R2 radius. So that is with respect to derivating with respect to R2. So the total deriving with respect to R2. So finally we got the critical radius of insulation for cylinder is K by H naught. This is very important term, very important. So R2 is nothing but critical radius of insulation. So R2 is equal to RC is equal to K by H naught. So R2 is nothing but RC is nothing but critical radius of insulation K by H naught. So when we look at look at for sphere, R2 is the same term, but here just we are replaced with replace the areas only. Here 2 pi RL, here just we replace 4 pi R1 R2. Okay, just replace the areas, and finally the term for critical radius of insulation for sphere is 2K by H naught. Okay, 2K by H naught. So I want to give the a clear clarification about the critical radius of insulation. Actually, listen carefully. When we provide insulation, it decreases the heat loss. from system to surrounding and surrounding to system. This is the case. But when we provide a insulation of cylinder or sphere, cylinder or sphere, it does not decreases the it does not decreases the heat loss. It increases the heat rate. So after certain amount of thickness, it heat rate is maximum. When we add some insulation, it decreases. So after the maximum condition, it decreases the heat loss. That particular thickness, whenever heat rate is maximum, we call as critical radius of insulation. At that particular thickness, we call as a critical 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 thickness. Okay, so for critical radius of insulation for cylinder is K by H naught, and critical radius of insulation for cylinder is 2K by H naught. Okay, students. Now we will look at the take one example regarding to the critical radius of insulation for sphere and the cylinder. So here it is a problem given. Problem given. So what is the problem? First, you have to look at once. So calculate the critical radius of insulation for asbestos, and this thermal conductivity is 0.172 watt per meter Kelvin. Surround a pipe and expose it to room air at 300 Kelvin with the heat transfer coefficient is equal to 2.8 watt per meter Kelvin. And finally, what he is asked to calculate the heat loss, that is nothing but Q. He asked a Q value from a 475 Kelvin heat loss. Sorry, calculate the heat loss from a 475 Kelvin 60 diameter pipe when covered with critical radius of insulation and without insulation. Okay, so with and without insulation, first of all, you have to observe here one thing. This is a radius, that is nothing but first of all, thermal conductivity is given. What is the given data he has? T1 is equal to 475 and T2 is equal to 300 Kelvin. Okay, here. So critical radius of insulation for thermal conductivity, surrounding pipe and exposed to room air at 300 Kelvin. That is nothing but surrounding temperature is T2, and H heat transfer coefficient, and heat loss calculate is nothing but T1. So he is given diameter. So R1 is equal to D by 2. The critical radius of insulation R is equal to K by H naught per cylinder. Put the values, and this is the radius of insulation, critical radius of insulation per cylinder. And with the Q, he wants to calculate the heat loss. So Q is equal to, already we know that formula. We know that formula. What is that? 2 pi, because of we are taken cylinder, 2 pi into T1 minus T2 by log of R naught by R1 by K, 1 by H naught into RC. Because of this is per cylinder, and just put the all values here and got the values of heat loss per cylinder. With insulation, when we take without insulation, just take the Newton's law of cooling equation. H naught into what is the area of the cylinder, 2 pi R, and the difference of temperature is T1 by T2. So this is the without insulation, right? Here, heat conduction with internal heat generation. In many cases, there is a heat generation with the system. Typical examples are, so electrical coils, resistance heater, nuclear reactor, combustion of fuel in the fuel bed of boiler furnace. Those are all the heat conduction with internal heat generation, right? Now we are going to see the plane wall with uniform heat generation. So what is meaning that? Consider a plane wall of thickness L of uniform thermal conductivity K, that the wall surface are maintained at temperature T1 and T2. It is assumed that the heat flow is one-dimensional steady state conditions. So this is the plane wall. This is one surface and this is second surface, and these two surfaces are maintained at the same temperature. So here is, for example, 50 degrees centigrade, and here also 50 degrees centigrade. And whenever the temperature is same, the thermal conductivity is also same. So this is one dimensional, and the assumptions are that it is a steady state. So that is nothing but properties does not change with respect to time. And this is a small element, and whenever the heat is generated in the direction of x plus dx, right? So heat conducted at a distance of x. This is taken from Fourier law. Q is equal to minus K into dt by dx. Whenever the heat is generated, Qg is equal to Q into volume. So volume take less area into dx, right? Because of area is meter square and distance dx is meter, so totally meter cube. Q into V is nothing but heat generated. The V taken in the form of area into dx. So heat conducted at a distance of x plus dx. Already we have no and there are some derivations like Cartesian coordinate equations, spherical coordinate system, and cylindrical coordinate system. So qx plus dx and this derivation is taken from Taylor's list qx plus dou by dou x of qx dx. So finally, energy balance on the element of the thickness is given by qx plus qg is equal to, so what is the in here, qx, and this is the in is qg is equal to what is the out term, qx plus 10. So total in is equal to total out. So qx plus qg is equal to qx plus, so what is the Taylor series, qx plus d by dx of qx dx. And finally we got the equation like that. T is equal to, this is, I want to tell this equation properly because of here we have the double derivations. So qg is equal to d by dx of qx dx. What is qg? Area into dx into qg is equal to d by dx of what is qx from 4L minus ka into dt by dx into dx. So finally we got d square t by, this is a differential with respect to dt by dx is nothing but minus ka into d square t by dx square into dx. So d square t by dx square plus qg is equal to, here cancel dx, and finally we got the equation like the d square t by dx square plus qg by k is equal to 0. So the first and second integration of equation. So this equation we have take and apply first integration. So when we apply the first integration, so dt by dx is equal to minus q by k. So with respect it is a first integration x plus and the constant term is c1, and we apply for second integration. So finally dt by dx is nothing but t is equal to minus q by k x square by 2 plus c1 into x plus c2. So when we apply the boundary conditions, at x is equal to 0, what is the temperature here? TW1. At x is equal to L and T2 is equal to TW2. Those are all the boundary conditions, and and we apply the boundary conditions and got the constant term values C1 and C2, and finally we got the equation is like that. So the maximum temperature has occurred at the center. This is the formula for maximum temperature. So whenever what I want to tell that, when the temperatures are same on the, when the temperature is same on the both sides, the temperature is maximum at the center of the plane at its distance at x is equal to L by 2. So when x is equal to L by 2, the temperature is maximum. So that is nothing but qg by 2k into L minus x into s at x is equal to L by 2 plus tw by plus TW. So this is the equation. So heat generation at the temperature is a uniform condition, plane wall with the uniform heat generation, and another one is critical radius of insulation. So both are very important. And yesterday class also initial boundary conditions. The topic is also very important. And the students, if you have any doubts, please ask me. And this is the entire unit 1 material. And this entire notes I told everything in our class notes. If you haven't read, please take the class notes from your friends. And everything I have done in I have done in our class, and everything I have made the derivations each and everything on the classroom board. So if you have any doubts, please call to me. And the final topic is the critical radius of insulation and plane wall with the uniform heat, uniform temperature. So those two topics are very important. And right now I will end this class, and next class we will start the new unit is new year. Okay students, thank you.